Okay, well, this is a test run for what hopefully will be streaming in the future regularly of my series called The Bite of Physics. I'm John Mallinckrodt. I'm the host for Bite of Physics. I put together weekly blurbs on topics out of physics, hopefully oriented toward the layperson, the interested layperson, and the talks go into more detail than you usually see when you go to, certainly when you go to a cutting edge type talk. We don't talk about cutting edge topics. We talk about very well established physics in the Bite of Physics, and so we can do so with a little, first of all, with a little more abandon in terms of, well, what should I say? A little less abandon, I guess, maybe. What we're talking about are, as I said, well-established things. But it doesn't require us then to wave our hands and use the kind of math and talk about things that are at the level that cutting edge topics usually are. We can go into a little more mathematical detail sometimes, or at least get into the weeds a bit more than you do on cutting edge talks, and convey a little bit about, what a serious topic science really is, that it is based on rigorous math. That's hard to do with cutting edge topics because the math is not only rigorous, but complicated and essential. And it is, I think, less essential as time goes on and people start to understand intuitively what's going on in well-established physics. So that's what we try to limit ourselves to. Stepping out on the line these last few weeks on a quantum mechanics series, which is both not my specialty. I'm learning a lot as I prepare to teach, as I always did when I was an active teacher, and we're also talking about something that's so it's not in my comfort zone exactly, and it's also not something that um, uh, it's also not something that I would normally think about doing in the Bite of Physics series, but we're giving it a try. So that's what we're doing today. And anybody down in the audience there, in the clubhouse audience, welcome to raise your hand, come up on stage, hang out, and interrupt me when necessary for points of clarification. Let's launch into today's talk, and it is on it's on the slides there at the top of the page, number 63, Quantum Mechanics Part 3, Free Particle Wave Functions. If you open that up, you'll see, as always, there's links to, on the page, there's links now to all of the previous Bites of Physics, links to my Nibbles of Physics series, which is a very short and irregular collection at the moment. And then just a link to all of my public documents, which include a lot of little treatises that I've put together on topics that interest me. Often, I confess, from my interactions with flat earthers who always raise um, really interesting points that I think deserve answers, and that often lead me into interesting new projects like taking pictures of the sun all day and stuff like
Blasphemy.
that. And like what, Groundsel?
I said blasphemy.
Blasphemy. Yeah, right. That's pretty much true. I got kicked out of the flat Earth room this week. Got banned from it, so I guess I won't be trying to help them anymore. Let's so go to page 2 there. Just a brief review. Last week we talked about we have been talking about what are called bound wave functions, the wave functions that represent particles that are bound in what we call a potential energy well. It really means that they are bound to a region of space by forces that are large enough to keep them from getting away from that region of space. And you can think of it like a roller coaster um, oscillating back and forth between two peaks on the roller coaster, because it just on the roller coaster track, because it doesn't have enough energy to get over either of those peaks. But of course, if you gave it a big enough shove, gave it some more energy, then it would be able to get over those peaks and escape that potential well, as we call it, that it's in. So we've been talking about the quantum mechanical wave functions for bound particles, and last week we introduced this idea of kind of a complicated square well, as it's called. A square well is just a well that has kind of hard walls. The particle can move freely within the well, but then it encounters a force large enough to classically immediately bounce off of, turn around, and keep going, and then go in the other direction. And we've seen that quantum mechanically, the wave function extends somewhat into the region that classically would be forbidden, and that represents some possibility of actually finding the particle in that forbidden region, a place that it doesn't have enough energy to get to classically. In quantum mechanics, there's always these little uncertainty things going on. We'll meet more of that today. And we took that potential well and we divided it. We put a barrier in between, kind of turning it into two potential wells. Classically, a particle in that potential well would have to be on one side or the other of the barrier in that top middle frame, for instance. Um, and that changes the nature of the wave functions. We talked about the boundary conditions that determine the wave functions. When you introduce a barrier, the interesting thing is that it brings the lowest possible energy up, brings the second energy down, brings the third energy up, brings the fourth energy down. So they start to merge in pairs. And as that barrier gets bigger, as it does on the top right, and then bigger yet, as it does on the lower left, bigger yet on the lower center, and then bigger yet in the lower right, those energies continue to merge until they look really just kind of like, basically, there's two wave functions at each of two energies. They're not exactly the same energy, but they're very close. And then we extended that to many potential wells separated by barriers like this, and saw that in general what happens, like if you have six of these wells rather than two, that the lowest six energies kind of merge, the next six energies merge, etc., forming bands, energy bands, as they're often called. And it's really important in solid state physics, and we didn't take it any further, just because as an example of applying the things we learned about boundary conditions for wave functions. So let me stop there for a moment. That's just kind of a review of some of the stuff we've talked about. As always, encourage people to ask questions, encourage people to raise hands if you're down in the audience. You can ask questions in the chat, but I'm not as likely to see them. I just don't pay much attention, obviously. So any comments or questions about that? I won't wait long here because we probably are just moving on to the next thing. Okay, so let's move on into really today's talk then. What we're going to talk about today are the energy eigenfunctions for a free particle. In some ways, we probably should have started with this. This is a particle that's not in a potential well. It's a particle where that potential function is just flat, and we might as well set it equal to zero. It's a particle that is freely able to move throughout all of space. But as usual, just for these introductory things, we think about all of space being one-dimensional space. So just to make life a little simpler, we'll talk about a particle that is free to move anywhere along the x-axis. The x-axis being, whatever you want it to be, whatever this line is that the particle is able to move along. And the Schrodinger equation, we've already seen the so-called time-independent Schrodinger equation, which we use to solve for energy eigenfunctions in the ways that we did in the first two segments, is that equation at the top there. But if we set v equal to zero everywhere, then we lose that function of x, that v of x. V is in general a function of where you are along the line. If we get rid of that and just set it equal to zero everywhere, the equation simplifies into the second equation there. And I'll just remind you, what I've tried to do is I write the equation down in mathematical language, but all that equation really says is that I'm looking for a function that curves. D squared by dx squared means how much this function's curve. So it says the function psi, which is the wave function, curves in such a way that the negative amount that it curves is equal to a constant times the function itself. So if the function is positive, by the way, that constant is always positive. The energy of the particle will be positive. Its mass will be positive. The so-called reduced Planck's constant, h bar, in that expression is positive. So that's a positive constant. And if the function itself is positive, then this says the curvature of the function has to be negative. And if the function itself is negative, then that equation says the curvature has to be positive. But in general, it's just saying that the bigger the function, since that thing out front of on the right side of the equation, since that 2me over h bar squared is just a constant, this function, this equation just says that the curvature. Oh, got my phone talking to me. See if I can turn him off. Is just saying that the curvature of the function itself is proportional to the negative is proportional to the negative value of the function itself. In slightly more mathematical language, what it says is I'm looking for a function whose second derivative, that's what d squared by dx squared means mathematically, second derivative of that function is equal to the opposite of the function itself times the constant. And some of you may know that there are functions whose second derivative is equal to negative the function. Those functions are sines and cosines. That's the kind of most fundamental characteristic of the sine function and the cosine function is that when you take the second derivative of a sine function, you get negative sine function. And when you take the second derivative of the cosine function, you get negative cosine function. So the most general solution of that second order linear differential equation, homogeneous, I should add, differential equation, if you want big words, is that the function should be some arbitrary constant a times the cosine of the square root of that constant, square root of 2me over h bar, times x, plus some other arbitrary constant b times the sine of that same thing. That's just what you read off of that equation. Let me just stop there for a second. Is there a question about that? Okay, fine. I'm actually lingering too much on the math, so let's just go ahead and see what this means. Now, one thing I'm going to mention today, and this is probably the hardest part of it, is that in quantum mechanics, it turns out that the wave function has to have two values at every point in space. There's no way to write quantum mechanics without it dealing with a wave function that is actually a double valued function of position field. It's a field that is a double valued function of position. At every position, I have to have two numbers. And it's just convenient. It's extremely convenient, but it should be understood that it's mere convenience to use complex numbers to represent the wave function. In other words, I can just represent the wave function as a complex number. That means some real number plus some imaginary number. And as you may know, imaginary numbers are always some multiple of the square root of -1. When we take the square root of -1, we call that I, the imaginary number I. And it has all sorts of nice mathematical properties that we won't go into. It just turns out that it's very convenient to use the mathematics of complex numbers to describe it. So those constants A and B are in general complex constants. For instance, A might literally be something like 3 plus 5i. That would be a complex number. 3 plus 5 times the square root of -1. And B might be 2 minus 10 times the square root of -1. So those constants that's what we mean when we talk about a complex constant. And we'll see why we need two numbers, and we will talk about them as complex. But the main thing you should understand is that we need two numbers at every place. And we're going to see why in this period, in this lecture. I guess I'll just go ahead and call it. So on the next page, I'm going to show a couple things, and one thing is to see what happens if we set the constant b equal to I times a. So if and in particular, let's let a just be 1. We might as well, I should have probably just said that. Let's let a be 1, and let's let b be I times 1. That would make b just I. B would just be the square root of -1. If I do that, then the full time-dependent wave function represents a free particle traveling to the right toward positive x. And if I set b equal to negative IA, so if I set b equal to negative I in this case, it would represent a free particle traveling to the left. We're going to see that on the next page. So if you go to page 4, I'll pause here for a second, but we're going to now see how that works. Maybe some of the questions will be, I should maybe just delay until the next thing, but does anybody have a comment or question? Oh, Andy, you're here. Did you have a comment or question, or are you just unmuted, or do I need to PTR? Oh, I see.
Am I
Andy.
unmuted?
You are unmuted, I believe. There you are. That's fine. Don't mind that.
That was accidental.
Be even better if you had a question, but okay, they'll probably come up here because now I'm gonna just show you what that means, and maybe we can stop after this next slide too. So I'm going to show you now at least a snapshot of a low and definite energy free particle. So for now, just remember that for a free particle, we have sines and cosines. And if I have a low and definite energy free particle, it may or may not, but if it does move in one direction, it moves in the direction of the imaginary part. If you look at those two snapshots down at the bottom of this page, in the one on the left, the imaginary part is just a little bit to the right of the real part. And because it leads, that's telling you that that wave is going to move with time to the right. Whereas the other snapshot on the right, I should have probably put these on the other side of each other. The one on the lower right has the imaginary part a little bit to the left of the real part. And that wave is going to move to the left for reasons that you have no reason to know yet, because we haven't talked about the so-called time-dependent Schrodinger equation, which we'll do next week. But for now, it's enough just to know that if you see a wave like that with the imaginary part kind of to one side of the real part, that's the direction that wave's going to move. And you can click on either one of those images and bring up a little movie clip, and you'll see the particle moving. Now, in each one of those graphs, represent a relatively low energy particle. Up at the top, there's an energy graph. And you can see, I think, that the energy here, the green bar is barely above 0. It's labeled 0.05 in some units, but we're going to look at some higher energy wave functions as well on the next slide. So that's what you're seeing in those two clips. Now, coming back up to the top, I'll just ask you to remember that the wave function tells us about the probability of finding the particle at any given place. And to be a little more specific than we've been before, the way you find that probability is by taking the wave function itself and then taking what's called the complex conjugate of the wave function and multiplying them together. And taking the complex conjugate of something just means changing the sign of all of the imaginary parts. So I'm just telling you that. I've done that there in the little inset at the upper right. And I'm telling you that the result for this kind of a wave function is that I just get the square of a. I get a squared. In other words, the probability of finding this particle at any given x is the same for all x's. So just the takeaway from this slide, you don't have to look at that math at all, is that because these sine waves extend out to infinity in both directions, and because of the way we actually find the probability of finding a particle, um, the probability of finding that particle at any given place is exactly the same as the probability of finding it any other place, which is kind of a way of saying we have no idea, absolutely no idea where that particle is. It could literally be anywhere. And it turns out, as we're going to see, that's because we know its momentum exactly. If we know its energy, that's kinetic energy, then we know its momentum exactly. And it turns out the only way to exactly know the momentum of a particle is to have no idea where it is. And that's just an instance of what's called the Heisenberg uncertainty principle. And so you're seeing what the Heisenberg uncertainty principle is based on here. It's based on the fact that only a pure sine wave has a pure energy, and a pure energy means a pure momentum, in this case for a free particle. And knowing the momentum exactly, as you can only do with an infinite sine wave, necessarily means that you have no idea where that particle is. So that's the Heisenberg uncertainty principle. That's a kind of a key, important, and hopefully kind of enlightening point. You're kind of seeing the origins, and we're going to see even a little more explicitly how the Heisenberg uncertainty principle works as we talk about localized particles in a moment. So let me stop there and see if there's any comments or questions.
So the mathematician in me is kind of itching. This conclusion that we've reached, that the probability is a constant, so it's independent of x. Does it not depend on the initial choice that we've made, that A is 1 and B is I? Is it not like if we changed those numbers, would it not change the result?
Yes, it would. So let me briefly, and we're gonna kind of do that, not so much this week, but next week. Let me just point out. So I've told you that if I do those two things, if I let B be IA, if I let B be IA, then I get a wave traveling purely to the right. If I let B equal negative IA, then I get a wave traveling purely to the left. But what if I set, for instance, I could set B equal to 0. If I set B equal to 0, then there is no, if I set A equal to 1, so literally 1, the real number 1, and I set B equal to 0, that's a wave function. And it's just a pure real, it's just like one of those red sine waves down at the bottom of this page. We're not really in a position yet to understand this, but a wave function like that doesn't move. It changes with time, but it represents actually a superposition. And well, maybe this is good to say. Suppose I added the wave function at the lower left there on this page to the wave function at the lower right. I would now have a superposition of two particles, one traveling to the right with some momentum and one traveling to the left with exactly the same momentum. And that superposition, I think you can see, would have no imaginary part, because the real part would be the same thing. The imaginary part would be 180 degrees out of phase, and it would cancel to 0 if I add the two imaginary parts in those graphs. Everywhere the imaginary part in one is high, the other one is low. And so it cancels exactly to 0. And if I then operated on that with the so-called time-dependent Schrodinger equation, which we'll do next week, you would see that purely real wave function just gets larger in amplitude and then smaller, and then it actually goes through zero, and then it goes to negative values or the opposite values. It's what we call a standing wave. And a standing wave is what you get when you have two equal amplitude, opposite propagating waves. So the sum of those two wave functions gives me a valid wave function, and that wave function is represented by a standing wave now. That gives me places now where the particle can never be found, and other places where it's more likely to be found. Just like a guitar string. Those of you who are guitarists, if you pluck your guitar and put your finger on the 12th fret, you form a standing wave. That's a standing wave of two oppositely propagating waves that has a place that never vibrates in the middle, and the two sides are going up and down, and then down and up and down and up. And you can form standing waves of different frequencies by holding your finger at the 7th fret, 5th fret, down almost to the 4th fret, and so on. The same kind of thing. Does that kind of get at your... And maybe I'll just say, you can do lots of things. So you can even add wave functions of different energies. That's what we're going to spend the rest of this period doing it, in order to create wave functions that are localized. That's the aim now. How do we represent a particle that we do know something about the position of? That's the rest of this period. Okay. Anybody's brain full yet? Oh, we've got Emily Nether down there. I have to be really careful about my symmetries. Okay. All right. So let's move on to the next page. And all I'm doing now in these next. By the way, once again, you can click on those figures and they'll go into motion. There's gift or little movies behind each one of them. So on the next page, page 5, I'm just showing higher energy free particles. If I make the energy higher, if you know a little bit about how those sines and cosines work, if the energy gets higher, then that constant in the sines and cosines gets bigger, and that means you have to go through less x to go through one full cycle. So the wavelength gets progressively smaller. Indeed, you can really read off. I won't go through the math, but it's pretty easy if you know how to do it. The wavelength you can read right off of the wave function itself. And it's 2 pi times h bar, the so-called reduced Planck's constant, divided by the square root of 2m times E, where that E is the kinetic energy here, because it's a free particle. It's the only energy it has is its kinetic energy. Now, the reduced Planck's constant is called that because it is Planck's constant divided by 2 pi. So when I multiply the reduced Planck's constant by 2 pi, I just get Planck's constant. And that square root of 2me is just the momentum of the particle. You may know that the kinetic energy is 1/2 mv squared. So if I multiply 1/2 mv squared by 2m, I just get m squared v squared. And if I take the square root of m squared v squared, I get mv. And the mass of an object times its velocity is what we call in classical physics the momentum. And I should mention here for a moment that we are doing classical, this is non-relativistic quantum mechanics. I should point that out because there is relativistic quantum mechanics as well. This is not what we're doing. We're doing the kind of quantum mechanics that's suitable for particles that aren't moving too fast. So that's really what we are restricted to here. And down at the bottom of this page, I'm showing now a particle. In the previous page, the energy was 0.05. On this page at the lower left, the energy is 0.2, so 4 times as big. And then the energy on the right is 0.5, so 10 times as big. And you can see that the wavelength is getting progressively smaller. In fact, the wavelength of that picture at the lower left is exactly half the wavelength of the one on the previous page, because the energy is 4 times as great. And you can look at that formula at the top and see when I take the square root of something that's 4 times as big, I get something that's 2 times as big. And the wavelength is now half as big because that energy is in the denominator. Okay, any comments on
Uh,
that?
just very quickly, the factor square root of 2, where does it go in this equation? Does it go inside P?
I'm not sure I know what you mean. What do you mean?
So I'm nerding around. You have
Mm-hmm.
lambda, and that's 2 pi h bar over the square root of 2me, and then we said E is equal to mc squared, right?
Oh, no. I said E is equal to 1/2 mv squared. This is
Oh, 1/2
non-relative.
mc squared. Okay, that's what
Yeah,
happens. Okay,
yeah,
okay,
yeah.
okay, okay.
Yeah, this is non-relativistic quantum mechanics. If it were relativistic quantum mechanics, then we would know about things like mc squared and be dealing with that, but we're not. And that's really kind of important to keep in mind as we go forward. Purely non-relativistic quantum mechanics, the kind that Bohr and everybody else did at the beginning. Relativistic quantum mechanics gets harder. Okay, so moving on to slide 6. It's sometimes useful. In fact, it's always useful. It's more useful than what we've done so far to, rather than showing plots as I've done on the previous 2 pages of the real part and the imaginary part, just these 2 numbers, right? We represent them as real and imaginary, but they're just these 2 numbers that we use to represent the wave function. It's useful to take that really seriously, kind of into the complex plane, as it's called, and represent the wave function not as real part and imaginary part, but as amplitude and phase, where the phase of the wave function just represents how much, so for instance, there's a color wheel there. And think of the horizontal axis as being the real part of the wave function, the vertical axis being the imaginary part. So if you're over on the right side, you're talking about the positive side of the real axis. Numbers along that direction are purely real and positive. Numbers over on the other side, horizontally, are purely real but negative. Numbers that go upward from the center are positive imaginary numbers. They're numbers like I, or 5i, 7i. Numbers going down from there are negative imaginary, like negative 4i, negative 7i, etc. But you can have coefficients that are things like 3 plus 1i. Well, 3 plus 1i is mostly real, a little bit imaginary. If I go over 3 in the real direction and then up 1 in the imaginary direction to represent that 1i, I'm still red-ish, but I'm kind of heading into the yellow territory. So I would color that a place with numbers like that kind of yellowish red, or orangish, I guess is what we call that, right? um, and so on, right? A number like -2 plus 3i, I would go -2 in the real direction. That would be to the left. And then I would go up 3, and I'd be in the kind of yellow-green area. So I would color that thing, that place, kind of yellow-green. And then in conjunction with that, with the phase, I also define the amplitude just to be the square, basically a Pythagorean theorem thing. Just do what I did before. Suppose I had 4 plus 3i. I go 4 out in the positive real direction and 3 up in the positive imaginary direction. And that would lead me to a point that is now 5 units away from the center. 4 out, 3 up. That's a Pythagorean right triangle, a 3, 4, 5 right triangle. The distance of the hypotenuse from the point up there at 4 plus 3i back to the center has a magnitude of, or an amplitude as we call it, of 5. So I can just represent 4 plus 3i as 5 at some angle, and that angle would be about 37 degrees counterclockwise from the real axis. That's the kind of by convention the way we do it. So I just color things that way. And so I've shown an alternate way of looking at a middle energy 0.2 I think again 0.2 energy particle in terms of phase. If you click on that diagram now, what you'll see, you won't see sine waves now. Excuse me. You'll just see a constant amplitude. That's the black line at the top, with phase moving to the right. And it might be worth just clicking on that, and if you can, taking a look at that movie clip. But what you will see is nothing but that colored phase bar moving to the right, showing that sine and cosine wave that represents the real and imaginary part are moving to the right, moving the phase with them as they go. Okay, this is terribly important. I do want to just make you aware of that, because you'll see phase and amplitude kinds of things from time to time as we go on. But just realize that just represents a real sine wave moving to the right with a imaginary sine wave leading it, because the imaginary one always leads in situations like this, by 90 degrees, right? And that's kind of important too. The imaginary part in this case is leading exactly by 1/4 of a cycle, 90 degrees if you want. Questions on that? Okay, now it gets more fun, a little more quantitative, a little more qualitative again. But so let's go on to the meat of this lecture, which is about how we talk about particles that we do know something about the location of. And this brings up the important topic of wave packets. This is critically important here. The idea is, first of all, we've seen that free particles of definite momentum or kinetic energy are equally likely to be literally anywhere. So we want to be able to figure out how to represent a particle whose location is not completely unknown. We want to do that. So we need a wave function that has an appreciable amplitude only in a limited region. I don't really so much care about its phase, but I want its amplitude to be appreciable only in a limited region, because the amplitude is proportional. Actually, if I square the amplitude, I get the probability of finding the particle at any given place. So we have to, and amazingly enough, can construct any desired wave function at all. You tell me the wave function you want, I can construct that wave function by adding energy eigenfunctions. That is to say, in the case of free particles, infinite sine waves. I can construct any function out of an infinite number of sine waves of different wavelengths, if I give them the proper amplitudes and phases. So I'm literally saying I can add a bunch of sine waves and get a function that is zero everywhere except a limited region. So these are sine waves that extend out infinitely far, but when I add them all up, they completely cancel everywhere except in a limited region. That should seem, if you think about it, I want you to think, that sounds crazy. How could I add a bunch of sine waves that extend to infinity and get them to add up to zero at every location along the x-axis, except, say, in this, over this 1 inch. In fact, I can do the following. This is what I can actually do. I can actually construct a function that is zero everywhere except at one point on the x-axis. I can construct a function like that. That's called a delta function. I can construct a delta function, a function that's zero everywhere except at a single point by adding sine waves. That should be amazing. And we're not going to do that today, but I think you're going to see how we could do that. So the little diagram at the bottom of this page represents kind of how one, for instance, could construct what's called a square wave out of sine waves. This is pretty easy. You just start with a lot of a big sine wave that's kind of like the square wave. And then you add some other sine wave that kind of brings the tops down, and brings the bottoms up, and then you add more and more, and you have to kind of tweak the phases. You have to decide which frequencies you want, but you end up making. Notice there, it's not exactly a square wave. And the only reason it's not exactly a square wave is because I've cut off my series at some point. I could, by adding sine waves out to infinity, I could make a literal square wave out of those things. So let me stop there for a sec before we move on. See, I'm sorry, there's a couple guys waiting to get on stage. Let me bring them up. Logic Guy and Benjamin. See if we get them up here. I don't know how long I've been ignoring them. There's Benjamin anyway. Try Logic Guy again. So Benjamin, what have you got?
John.
Are you just waiting to
Just a
pounce, or have you
comment
got
real
something?
quick.
Yeah.
Don't you mean any periodic function?
No, I don't. But it's a good point. We're getting all of the things we're going to do from here on the rest of the day are, in fact, going to be examples of constructing only periodic functions. But if you actually literally extend the idea of Fourier synthesis to adding up sine waves of every possible wavelength, not just discrete wavelengths, but every possible wavelength, then you can actually literally construct a delta function, a non-periodic delta function out of that. And I'll kind of show you how that happens here in a couple slides. That's a good question, though. Thank you. Logic Guy, I tried inviting you a couple times. Maybe you're... Anyway, okay. If you're not getting it, you might... let me mod up a couple more guys here just to cover my ass if I get booted out of my own room and all that. And maybe also to try Logic Guy if he's still around. I can never exactly tell. Okay, let's move on then to slide 8. So here's an example of synthesizing a wave packet. And what I'm going to mean here is I'm going to construct, this is kind of pretty typical, to construct a Gaussian wave packet. So this is a wave packet that has appreciable amplitude only in a region, only in a small region, and the amplitude takes the form of a Gaussian or something like a Gaussian. You probably know what Gaussian curves are if you've ever got an F in math. Or something else, right? Somebody said, "Oh, that's way out on the Gaussian curve," or an A for that matter. Either side, right? If you got a C, you're right there at the center of the bell curve and all that kind of stuff. So we're going to try to construct something like that. So what I'm going to do is this app that you're seeing there, and I'm sorry it's so small. All of these things are probably better viewed on laptops. I apologize for those of you who are probably looking at it on a phone. At the left side of the screen there, what I'm presented with at the top bar is a bunch of sine waves. There's a little bar that I haven't used. A1, it says A1, and then next to it A2, A3, A4, A5, A6, A7, A8, 9, 10. I guess it goes up to 11. There's 11 bars that I can move up or down, and each one of those bars represents the amplitude of a sine wave of a different wavelength. A1, if I brought the A1 bar up, I would create a sine wave that starts at in the frame below. It would start at the far left 0. It would go up to a maximum in the middle, and it would come down to 0 at the far right. I believe. Is that right? 1, 2, 3, 4, 5, 6. Yes, that's right. That's what it would do. A2 would go up and then come down. Actually, maybe I'm saying that wrong. Well, at any rate, I may be off by a factor of one. Anyway, the point is that A1 is some wavelength that starts at zero, ends at zero. A2 is twice that wavelength. Half that wavelength. A3 is a third of that wavelength. A4, a fourth, etc. So I'm bringing up A6. I'm bringing up the amplitude on a sine wave that has 1/6 the wavelength of the primary. So I guess actually I lied when I said that about the first. A1 would represent a sine wave that starts at zero, goes up to a maximum at a quarter way, comes back to zero halfway, down to negative a maximum of 3/4 of the way, and then comes back to zero. That's what A1 would give me. And A2 would give me something that goes uh, up and down, comes back to zero in the middle, and then goes up and down and comes back to zero at the end. So A6 is one that does that 6 times rather than just 1 or 2 times. And you can see the result right there. Now, what I want to do is I want to try to get rid of the stuff on the sides here. And it turns out that a good way to start doing that is to bring up a little A5 and a little A7. So if you go up to the top right, you'll see I bring up a little bit of A5, and you can see the result down. So the two waves are now shown in the middle frame. The result is shown in the bottom of that frame, that black squiggly line. You can see that just by bringing up A5, I've reduced the amount of the wave out at the ends, and I've kind of boosted the amount of wave in the middle there. And I think you can see why that happens. It's because at the middle, those two waves are exactly in phase. But as I get further and further away, because they're different wavelengths, they get more and more out of phase, so they start kind of canceling each other. One problem is, as Benjamin alluded to, if I go much further to the right or to the left, those waves are going to come back into phase. So I'm going to see this little localized wave packet that I'm building repeated out there. So that is important to keep in mind. That's a good question, an important thing to think about. I can make things a little better by bringing up a little A7 as well. In fact, it turns out that the way to build a wave packet is to start with something and then bring up a lot of the two components just to either side. And you can see the result there. I'm doing a much better job now. I've really canceled out stuff at the ends and left myself with a pretty big amplitude wave just in the middle. So I'm doing pretty well. If you move on, oh, and by the way, you can play with this yourself. That's the link. That link down there is linked to the software that I was playing. I, literally played with this, and it's got lots of other buttons and dials you can play with as well. So I encourage you to check that out yourself. If you go on to slide 9, I then bring up a little bit of A4 and A8, and you see that makes it better yet. That's top right, top left. Bring up a little A4 and A8, getting to look pretty good. A little bit of A3 and A9 over at the top right, sorry. And then a little of the two on either side of that, bottom left. And then a little bit of the A1 and the A11. And what am I left with at the end? By the time I get to adding up all those 11 components, I now have a wave function that's very nicely localized. It's kind of sinusoidal-like, but it's limited to the middle region there. I've really pretty much made the wave function zero everywhere else. And once again, I would just remind you that, as Benjamin mentioned, if you go off in either the positive or the negative direction, you're going to see that same little wave packet that I've constructed there repeated, and it'll repeat every so often, every that often off to the side. That's what Benjamin meant when he was talking about, won't I be constructing periodic
Can I just take a minute to prove that it has to be periodic?
Sure, go ahead.
So whatever arbitrary waveform you create of finite length, if I double the length, I'll get a repetition of the same shape.
Yeah, that's right. Anything that has twice the period of something will also have the period of that first thing, right? I'm sorry, twice, half. Anything that has half the period will cycle not only twice as fast, but also just as fast, and 3 times and 4 times. So all of
So
those
aren't all
components
Fourier
cycle.
constructs periodic by definition?
That's right. So the kind of Fourier synthesis that we're doing here, where we're using multiples of a lowest frequency, that's true. But when we start talking about what happens in what are we doing? We have an infinite vector space in the language of math. We're not talking. Oh, I guess we have an infinite vector space here too. But in the case of quantum mechanics, what we're going to be able to do is to add up not just multiples of a lowest frequency, but every conceivable frequency. That's the difference. And in some ways, you might want to think that that's just multiples, but I would challenge you to find what those are multiples of, because we're using every conceivable one. So anyway, that's the result, and you do get that periodicity. Right about now, we're well in the next couple. We'll see how we can get rid of that periodicity thing. So on slide 10, well, let me just first of all ask: are there any other comments on this? We're getting pretty close to the end of this one. On slide 10,
if physics
go ahead.
is quantum at root, how do you have arbitrary frequencies?
You mean aren't the frequencies quantized? Is that what you're saying?
Well, yeah. I mean, you either believe that it's quantum at base or not, and if you want arbitrary frequencies, you need to reject quantum at base.
Well, there's no indication that frequencies are quantized. Let me just put it that way. If time itself is quantized, which some people, is something that some people look at, certainly seems like a plausible conjecture, then something has to give at some point, but it gives at a point that's well beyond our ability to look at experimentally, because the quantum of time, if it is one, I think it's something like 10 to the minus 40th seconds or something, maybe 30th. It's way smaller than anything we have any capability of experimentally probing at the moment. So there's no experimental indication that time is quantized. But it's a reasonable conjecture, if you believe in the idea of quantum physics. Quantum physics doesn't necessarily mean that everything is quantized, but it certainly does mean that some things are. Okay, so let's move on to slide 10. In slide 10, I'm using a different version of the same program that gives me a better way of doing this. So what this shows you now, I'm just going to notice that my selection of the amplitudes of those frequencies is itself kind of a wave packety thing. It has a Gaussian shape to it. To construct my wave packet, I chose frequencies with amplitudes that fit in kind of a Gaussian amplitude, and so a Gaussian envelope, as it's called. So what I'm doing here is I'm just showing you the envelope, at the right of this page. Sorry, at the left of this page, I'm showing a Gaussian envelope that will decide the amplitudes of the various frequency wavelength components that I'm going to add. I'm going to add a lot of, what is that? I can't even see it myself. Anyway, whatever that middle wavelength is. Oh, I guess that, forget about the labeling is going to be confusing. It's in terms of numbers, that the 2 pi, the 4 pi, etc. Forget about that. Just look at the bars. The bars are showing me the discrete wavelengths that I have to choose from, and I choose one relatively short wavelength, and then a little bit of each component on each side, just like I did before, a little less of each component to the side of that, etc. And then I kind of come down. So I get a Gaussian selection of wavelengths. And remember that those wavelengths correspond to momentum. I'm now building a wave function that I don't know the momentum of. It's built from wave functions representing different definite wave functions, but now I have a wave function that if I were to measure its momentum, I would only know that the most probable momentum is the one represented by that largest amplitude, and I would get lower probabilities for momenta on either side of it. But because of the choice of that envelope, I end up producing a wave packet, and you see it down there at the bottom. The middle frame is once again just showing you all of the individual sine functions, and you can kind of see how they're in phase at the center, and then they just go wildly out of phase, kind of canceling each other everywhere. But then there's these echoes, these little echoes where they come back into phase that Benjamin was talking about before. So I really have constructed a periodic set of wave packets by doing this. Okay. Now, suppose I used that same envelope, but I allowed myself to use twice as many discrete wavelengths. So I put another wavelength halfway between each one of those. That's what you get over there at the top right. The top right, now I have the same envelope, but now I'm allowing myself to use sine waves with much more closely spaced wavelengths. As a result, I get the exact same wave packet that I got before. The wave in it looks pretty much exactly the same. The envelope of that wave packet looks pretty much exactly the same. The only thing that's happened is that the overall periodicity has gotten longer. In other words, the little copies of that central wave packet have been moved out to the right and the left because of the fact that I'm allowing myself to use twice as many discrete wavelengths. And at the bottom there, I've chosen now 4 times as many, I think, or something. Anyway, a lot more. Now, same envelope for my choices, same basic, if you want to say, uncertainty in the momentum. Notice that the width of that envelope at the top represents kind of the region in which I would expect to find the particle to have its wavelength, and therefore its momentum. So its momentum is confined to a region of momentum space. That wavelength space is really momentum space. It's confined to a region of momentum space. The resulting wave packet is confined to a region of configuration space, as it's often called. That's just fancy word for location in space. And the echoes have been moved even further off to the right and left. Now, if I continue that process and let myself choose not just finer and finer spaced wavelengths, but literally any wavelength at all, then those echoes get moved literally to infinity, and I'm no longer describing a periodic function. I've now created a function that is non-zero only in that center region with the wave packet there. And you just have to believe me on that, but I think that should make some sense. Let's see, questions? Okay. All right. So now we want to really get serious about that, about the envelope itself. Notice that if I do the same thing, now I'm going to use the very fine spacing. If I narrow the envelope in momentum space, so now I'm not using as many momentum wavelengths, therefore momentums, as I was before. It's a narrower distribution of momentums wavelengths leads to a wider envelope on the wave packet itself. So the cost of making the momentum more certain, which I do at the left there, is to make the position less certain. And over on the right, I make the momentum more uncertain. I add wavelengths over a large range, and therefore I have very little, there's a high probability of measuring that particle to have any of those momentums, because the amplitudes of those momentum eigenfunctions correspond to the probabilities of finding them. As I broaden that distribution of momentum eigenfunctions, wavelengths, I narrow the wave packet that I produce. So by allowing myself more uncertainty in the momentum, I get myself more certainty about the position. And I'll just say this, you might imagine, what if I wanted to literally create a delta function, a particle that could only exist at x equals 0, or whatever that x, 0, I guess, is. What would I do? Well, I would just add equal amplitudes of every wavelength. I would take every wavelength you can write out, real numbers, rational, irrational numbers, pi, I'd have a wavelength of pi, I'd have a wavelength of E, I'd have a wavelength of 3, 3.1, 3.11, 3.111, 3.11111, etc. Every wavelength you can write the number for, and even those you can't. And I would add them all up with equal amplitudes, and I would get a function with 0 everywhere except at x equals 0, where it's infinite. That's called a delta function. But this is absolutely, you now know, at least qualitatively, the mathematics behind the Heisenberg uncertainty principle. This is the Heisenberg uncertainty principle, the product of the uncertainty in the momentum and the uncertainty in the position is always greater than or equal to, and the greater than is, maybe we'll talk about that some other time. Probably won't. Planck's constant divided by 2. Actually, Planck's constant divided by 4 pi. The reduced Planck's constant divided by 2. But that's getting too mathematical. Okay, so I really want to just pause there for a second and really emphasize, this thing we've talked about now is really important. This whole construction of wave packets, the way you have to use different momenta to get localization, and the more wavelengths you use, the more uncertainty there is in the momentum, the more localized you can make the wave packet, and therefore the more certain the position. That's a really key and early result of quantum mechanics, and this is literally where it comes from. Okay, so maybe moving on to slide 12, the last slide with any meat here. I'm just kind of showing you what happens if I take the same envelope for my choice of waves, that how much wave I'm going to add, and I now move them. If I take it, I started out there kind of with choosing the peak wavelength was one in the kind of the middle of that range, but now I'm taking that same distribution, I'm just sliding it to the left on the left side there. That's sliding it towards longer wavelengths. Well, the fact that the envelope of those momentum is the same means that the envelope of my wave packet will also be the same. I can slide that same envelope for the momentum to the right, as I've done on the right, toward higher frequency, shorter wavelength, I should say, waves. And once again, I get the same envelope. The only difference is that the actual wave function itself is oscillating now with a shorter wavelength, because the kind of fundamental wavelength that you see in that wave packet reflects the center of the distribution. On the right, it's a long wavelength center. On the left, it's a long wavelength center, and on the right, it's a short wavelength center. And so the only difference we see in the wave function is that on the left, it's a long wavelength wave oscillating within the envelope, and on the right, it's a short wavelength wave oscillating within the envelope. That's the effect of shifting my Gaussian for the momentum. And with those 3 slides, if you just look at the results of those 3 slides, the first one showing how we go from periodic to non-periodic, really. The second one showing the effect of broadening that choice of wavelengths, and the third one representing what happens when we move the center of that choice of wavelengths, on how the effect on the envelope of the wave packet and the wave that's actually um, within that envelope. So that's pretty much done. I'll just maybe slide 13 just as to go on next time. Next time I'm going to put those wave packets in motion. And what we're going to see is that when we apply the time dependent Schrodinger equation to a wave packet, that in general it moves and it broadens. So if you start out with a wave packet that kind of says, oh, the particle is somewhere in this region, that over time, that Gaussian wave packet will broaden. We will lose understanding about where the particle is, even though we don't lose understanding about the momentum. So what happens with time in the particular case of a free particle is the uncertainty in the momentum won't change, but the uncertainty in the position does. And it gets bigger. That's where the greater than, I guess, in the Heisenberg uncertainty principle comes from. And that's simply because, classically, you can understand that. If I have some uncertainty about how fast the particle is, then no matter how certain I am about where it is, I'm going to lose that certainty because I don't know how fast it's moving. So I don't know where it'll be later on. And that's what we'll talk about next time. And I'm done. So come on stage if you'd like to ask questions. Let me see. I don't see any other questions in there in the chat. So I'll just open it up to anybody on the stage. And raise your hands if you'd like to come up. Okay, I've done it again. I'm hoping. I really do. I know there was some math there, but I think the really key thing is kind of the understanding about how bringing up little bits of waves on each side kind of tends to cancel out to the sides, and that as you increase the density of those wavelengths that you can choose, you move the echoes out. And then just really the most important thing is that trade-off, that the more momenta, the more wavelengths you choose to build your wave packet, the tighter a wave packet you can build. And that is the Heisenberg uncertainty principle.
So if we look at all of this, for example, what is the real world equivalence or meaning of shifting the curve to the left? What, is it measuring more accurately? Is it giving it more or less energy? What are we doing so that the wave shifts to the left?
Right. So when I move the envelope, you mean to the left or the right? Is that what you're saying?
Yeah.
So in those pictures on page 12, right?
12.
When I shift the when I shift the envelope of the wavelengths that I'm choosing to the left, I'm going to longer wavelengths. That is to say that the wave packet I build will be built out of wave functions representing lower energy particles. So I know that if I measure the energy of that particle, it's likely to be lower because of that fact. Whereas the one on the right, where I've shifted to the right, those are shorter wavelength, higher energy things. If I measure the energy of that particle, it will represent a higher energy particle. So let me just let's talk about the evolution of these two things. Let's look at that actual wave function there at the bottom left and the bottom right. The bottom left represents a localized wave of relatively low energy because it has a relatively long wavelength. The one on the right represents a just as localized particle of higher energy because it has a smaller wavelength. Now, what do you imagine would happen? Let's suppose, and I haven't said this, but let's suppose that I'm also going to construct these wave functions. This requires doing a little more stuff, and we construct them in a way such that all of the waves that they're built out of are moving to the right. Let's suppose they're all moving to the right. Then what's going to happen? We're going to see when we use the time-dependent Schrodinger equation next week is that both of those packets will get larger as time. The envelopes will spread out as time goes on, but the center of the envelope for the one on the left will move more slowly than the center of the envelope for the one on the right, because after all, it represents a lower energy particle. And so the most likely place to find that after a while will not have moved as far as the one that has higher energy over on the right there. Does that make sense?
Oh, absolutely. Because I was wondering, what if you move all the way to the left, and then you will get something like a flat line, right? So this is an impossible situation where the particle has zero energy, but we are
Oh,
absolutely sure. Yeah.
right. Yeah, so we could play those games, and next week maybe we will. We'll see. We're going to see what happens. For instance, it's possible to construct a wave packet like that one on the left out of energy eigenfunctions, sines and cosines, such that they're moving equally to the left and right. Now, if I can make a standing wave out of that, I can construct that out of sines and cosines that are moving equally to the left and the right. And so this is what the packet that I would get. Maybe you can imagine that what I would then find after time would be two packets, one moving to the left and one moving to the right, each one of which has a lower amplitude. And that would represent the fact that at t equals 0, what this really was a superposition of two particles, one moving to the right, one moving to the left, with equal uncertainties in their momenta and equal certainties about and equal average energies. But as time goes on, then that thing will just split into two wave packets, two smaller wave packets moving to the left and right. In fact, what that thing may have been constructed from was two wave packets coming in from the left and right. And I might have just taken that picture at the moment when they collided. But there's no bouncing off. The wave functions just continue moving. And so a moment later, it will just be two wave packets moving off to the left and right without having distorted themselves at all, although they will be spreading. Wave packets always spread because of the spread of energies that goes into making them up. Yeah, so time dependence next time, and then probably with that, it's probably time to return and finish this thing up with the reason for putting it together in the first place. I think, Shamash, you probably got a better idea already about where tunneling comes from than you might have.
Oh,
But
absolutely. Yeah, definitely. Because we started with the fact that the wave function goes into the barrier. Like that was lecture 1. So
right,
we got
yeah,
there.
that's kind of all you need at some level. That's right. Okay, well, once again, maybe we'll just find a way to shut this down. Uh, Happy to entertain more questions if anyone wants to raise your hand. We're going soon. All right, so we're gonna replace this skipping record with another one and say goodbye, and we'll see you. Let's see. I have to wait a minute. I have to find out what the other skipping record's going to be today. What will it be? Oh, I don't know. Well, maybe it'll be this one. Sounds like a good skipping record. This really does sound like a good skipping record because I could only write lyrics to one verse, and I never intended to keep it around for very long.
I don't know why you
See you
call it a
next.
skipping record. We got new information today, and it
Yeah,
resolved the question we asked a year ago. That's
this
not.
is okay. Well, if you're not a skipping record, this is. See everybody next week. Bye. Oh, wait a minute. Sorry, screwed up. There we go.